Picture this. You're standing at the base of a towering, multi-million-dollar wind turbine. You're looking up at these massive steel towers, the colossal fiberglass blades.
Oh, yeah, heavy-duty gearboxes, the works. I mean, this is infrastructure built to withstand hurricane-force winds and brutal environmental extremes.
Right. But what actually brings a giant like that crashing to a halt, grinding its gears to dust, usually isn't a catastrophic storm.
No, it really isn't.
It's actually, it's a single drop of water or a speck of dirt no wider than a fraction of a human hair.
It sounds kind of absurd when you put it that way, but that really is the reality of industrial engineering. We build these massive monoliths of steel, but their Achilles heel is entirely microscopic.
It's wild. Well, welcome to the deep dive. Today, our mission is to decode a document that, on the surface, looks like a purely technical engineering spec sheet.
Yeah, the technical data sheet for Decus's standard series breathers.
Exactly. But we are not going to just read off a list of numbers today. What we're actually doing is uncovering the anatomy of the invisible lungs that protect the massive machinery powering your world.
I love that. Lungs is, it's the perfect way to frame this. Because anyone who works around heavy machinery, whether you're in automotive engineering, wind energy, or you manage massive power transformers, you know that machines have to breathe.
Wait, I want to stop you right there because I think a lot of people, myself included at first, picture a gearbox or a hydraulic reservoir as a completely sealed metal box.
Right, like a vault.
Yeah. Why does a machine need to breathe at all? I mean, why not just weld it shut so the dirt and water can't even get in?
That is a great question, and it really comes down to basic thermodynamics.
Okay.
So when a giant industrial gearbox starts running, the friction generates an enormous amount of heat. And as the oil and the air inside that sealed box heat up, they expand.
Oh, of course.
Yeah, and if the box is completely airtight, that pressure builds and builds until it literally blows the seals out of the joints just to escape.
Yikes, so it has to vent.
Exactly. Then, when the machine shuts down and cools off, the air inside contracts, which creates a vacuum that sucks outside air back in.
So it is quite literally exhaling when it gets hot and inhaling when it cools down.
Right. And if the air it inhales from, say, a factory floor or an outdoor power plant is carrying moisture or airborne dirt, those elements mix directly into the lubricants.
Which is bad news.
Very bad news. The oil degrades, rust forms on the steel gears, friction skyrockets, and your multi-million-dollar equipment dies a very sudden, very expensive death.
Wow. Which brings us to the first line of defense, these Decay Standard Series breathers.
Yep, the breathers.
The tech sheet outlines how these devices provide the fundamental protection for those vulnerable lubricants. But, to understand how they actually pull this off, we have to look at the sheer extremes they're designed to survive.
Oh, the environments we're talking about are rarely pleasant. We're looking at heavy manufacturing floors, paper mills, outdoor substations in the dead of winter.
Yeah, the temperature range listed on this spec sheet is staggering. They are engineered to operate in environments as cold as minus 20 degrees Fahrenheit, all the way up to a blistering 200 degrees Fahrenheit.
It's a huge swing.
It is. And while they're being frozen or practically boiled alive, they are maintaining a filter efficiency of, quote, 3 micrometers absolute. Now, I really want to dig into that terminology because absolute is a very specific engineering promise.
It is the most critical word in that sentence, actually.
Really?
Yeah, because in the world of commercial filtration, you usually encounter what's called a nominal rating.
Nominal.
A nominal 3-micron filter means it stops a good percentage of particles that size. Maybe 50%, maybe 80% on a good day.
Yeah.
It's a general guideline, like an average.
So a nominal filter is essentially a chain link fence.
That's a good way to look at it.
It'll keep most of the stray dogs out of your yard, but if a particularly small or determined dog comes along, it can still squeeze through the gaps?
That's exactly it. An absolute rating, however, changes the physics of the barrier entirely.
How so?
Well, 3 micrometers absolute means the material is engineered so that virtually 0 particles of that size or larger can pass through. Using your analogy, it's not a chain link fence anymore. It is a solid glass wall.
Oh, wow. And just for context for you listening, 3 micrometers is incredibly small. Like a single human red blood cell is roughly 7 or 8 micrometers across.
Right.
So this breather is standing guard in 200-degree heat, and the bouncer at the door is catching solid objects less than half the size of a blood cell.
The material engineering required to achieve that is just phenomenal. Think about what happens to physical materials under temperature extremes. Metal expands and contracts, plastics warp.
Seals degrade.
Exactly. But the internal geometry of this little plastic device has to hold its structural integrity perfectly.
Because if it doesn't,
If the filter media shifts or tears by even a fraction of a millimeter because of the heat, you live that absolute 3-micron barrier entirely.
okay, so that handles the solid threats, the microscopic grit, the dirt, the dust.
Yeah.
But as we established, there's a second enemy trying to get inside the machine, and it's arguably even more insidious, the moisture.
Ugh, water is the absolute bane of industrial lubricants.
Is it really that bad? I mean, don't oil and water naturally separate?
A lot of people assume that. They think oil and water just separate, like salad dressing.
Right.
But in a high-speed gearbox, they emulsify. They get whipped together.
Oh, I see.
And once water gets into the oil, it alters the viscosity, it causes oxidation, and most dangerously, it completely compromises that thin, microscopic film of lubrication that keeps the heavy metal gear teeth from grinding directly against each other.
So it's metal on metal.
Exactly, which destroys the machine.
Wow. Okay, so I was reading through the chemical makeup of the hydrophilic media inside these breathers, and the sheet identifies it simply as silica gel.
Yep, good old silica gel.
But what makes this brilliant isn't just that it traps water, it's the visual feedback. The silica gel is engineered to physically change color from blue to pink as it absorbs the moisture.
It acts as an active visual sponge.
And the simplicity of that is what really struck me. We are talking about highly complex industrial environments, right? Sensors and diagnostic computers everywhere.
Oh yeah, screens on every panel.
Yet this system takes the incredibly complex chemical process of atmospheric moisture absorption and turns it into a foolproof color code.
You have to consider the psychology of the maintenance worker on the factory floor here.
How do you mean?
Well, they might be managing hundreds of different machines across a sprawling facility. They do not have the time to plug a laptop into every single gearbox or take oil samples to a lab every afternoon just to find out if the breather is saturated.
Right, that would take forever.
Exactly. So with this, they can just walk past it. If the device is blue, it's breathing clean, dry air. If it's turned pink, the sponge is full, and it's time to screw on a new one.
That is so elegant. Let's look at the sheer scale of water absorption capacity across this product line, because I think it reveals how Decase engineers these for vastly different physical applications.
For sure. The scale is huge.
So the baseline miniature model, the DC-BB, contains just 1/10 of a pound of desiccant. It maxes out at holding about 0.8 fluid ounces of water.
Which is pretty small.
Yeah, that's barely a shot glass worth of moisture.
But which is perfectly adequate for a tiny, say, 2-gallon hydraulic lube reservoir that barely exhales.
Okay, that makes sense.
But if you move up the chart to the massive DC-4 model, you are looking at a unit packed with 2 full pounds of silica gel.
Wow.
Yeah, that single breather can trap a whopping 12 fluid ounces of water from the ambient air.
That is nearly an entire standard soda can's worth of pure water, just pulled out of thin air before it even has a chance to drip down and contaminate a 500-gallon storage tank.
And the passive nature of it is what prevents catastrophic failures.
Duh.
The machine breathes, the silica grabs the water, the color changes.
No moving parts to break.
None.
So we have this perfect internal environment. We've got the 3-micron glass wall for the dirt, and we've got the massive blue to pink sponge for the moisture.
The ultimate shield.
Right. But this raises a massive practical question. How does an engineer actually decide which one of these to bolt onto their machine?
It's a critical choice.
Well, I was looking at them,
It does.
but you are bumping up against the physical reality of fluid dynamics here. Look very closely at the header above those maximum airflow numbers.
Okay.
There is a specific condition applied to them. It says maximum airflow at delta P1 psi.
Delta P, the change in pressure.
Precisely, the pressure drop across the breather.
Okay, break that down for me.
When that gearbox cools down and inhales, it creates suction. The breather on top creates resistance against that suction.
Naturally, it's pulling air through a filter.
Right. If the resistance gets too high, if the breather is choking the airflow, the machine pulls harder and harder. Eventually, the suction becomes so strong, it will literally rip the rubber seals right out of the gearbox casing.
Oh, wow. So the engineers have to set a hard safety limit?
They do. They've decided that 1 pound per square inch of resistance is the maximum safe threshold before the machine starts damaging itself.
Okay, that makes sense. So both the tiny DC-BB and the larger DC-1 are being measured against that exact same 1 psi safety limit. Now, I want you to imagine these silica gel beads inside these plastic housings as a giant indoor ball pit.
Huh. Okay, I'm picturing a fast food play area.
Exactly.
Oh,
And the air has to physically weave its way through and around thousands of little plastic balls to get into the machine.
okay.
In the tiny DCBB model, the air only has to push through a very shallow layer, just a tenth of a pound of beads. Because the journey is so short, there isn't much friction.
So you can pull the air through that shallow ball pit relatively fast?
Right. At 5 cubic feet per minute before the friction builds up enough to hit that 1 psi danger limit.
Oh, I see exactly where this is going.
I bet you do. Now look at the larger DC-1.
It contains 3 times as much silica gel, so the ball pit is 3 times as deep.
Exactly. Pushing air through that massive deep bed of media inherently creates significantly more friction. It is a much harder journey for the air.
So to keep the pressure drop safely at that 1 psi limit, you have to pull the air through the deeper bed much slower.
You've got it. The DC-1 sacrifices a tiny bit of airflow speed, dropping to 4 cubic feet per minute. But the trade-off is massive.
Because it holds more water.
Yes. By having that deeper bed, you more than double your moisture trapping capacity. You jump from holding 0.8 ounces of water to 1.7 ounces.
That is a phenomenal piece of engineering logic. It's a literal, physical trade-off engineered into the architecture of the device.
It's all about balance.
You get a bigger sponge, but you have to pull the air through it more gently so you don't blow a seal on the equipment.
Which is exactly why there is a crucial warning note at the bottom of the sizing recommendations chart.
I saw that.
It tells the user that these airflow numbers are only a general guideline. Sizing an industrial breather isn't just a simple matter of walking up to a machine and saying, bigger is better.
Right. Note number 2 specifically calls out that you have to analyze ambient temperatures, humidity levels, and the frequency of airflow.
Yes, the frequency is key.
Because if you have a massive hydraulic cylinder that takes violent, rapid gulps of air every 5 seconds, you can't just slap the deepest bed of silica gel on it. The air won't move fast enough.
You'll choke the system. You have to understand the inhalation profile of your specific machine.
Oh, okay.
Are we talking about a slow, steady displacement like a 500-gallon storage tank slowly draining its fluid over a 4-hour shift?
Mm-hmm.
Or is it that rapid hydraulic cycling?
I see.
That operational profile dictates your choice of breather just as much as the volume of water you're trying to trap.
So we've solved the internal physics. We know how it traps the water, how it blocks the dirt, and how it safely manages the airflow.
The inside is sorted.
But having perfect internal chemistry doesn't mean anything if the physical box falls apart.
Oh, definitely not.
How do you build a plastic housing that holds this delicate process without cracking, shattering, or melting into a puddle when it's bolted to a vibrating 200-degree tank of toxic fluids?
The external ruggedness is just as critical as the internal filtration. And the materials list on this spec sheet reads like an armored vehicle's blueprint.
I was looking at that. The housing body is made of polycarbonate, which makes perfect sense because polycarbonate is highly impact resistant. But more importantly, it's completely clear.
Right, you need a transparent window to see the silica gel shift from blue to pink.
Exactly. But it's the structural components, the base and the top cap, that caught my attention. They aren't just molded plastic.
No, they're much tougher.
They use polypropylene and a very specific material called nylon 66 30% glass filled.
Ah, that glass-filled nylon is a marvel of material science.
Really? What makes it so special?
Well, when you inject microscopic glass fibers into nylon, those fibers act exactly like steel rebar inside concrete. They provide immense tensile strength and rigidity.
Why is that rigidity so important here, though? I mean, why not just use thick, standard nylon?
Because of the thermal expansion we talked about earlier. When you bolt a standard plastic thread into a metal gearbox and then heat that metal up to 200 degrees,
The standard plastic will warp.
it softens and deforms, yeah. And if the threads deform even slightly, you lose your airtight seal.
Oh, and then that 3-micron absolute filter is now useless because contaminated air is just leaking in through the warped threads.
Exactly. The glass-filled nylon refuses to warp under heat and mechanical stress, maintaining a perfect microscopic seal.
Wow. Speaking of those threaded connections, the spec sheet details how these actually attach to the machinery.
Let's talk about the threads.
For the miniature breathers, it uses a 38-inch multi-fit male thread with a built-in O-ring. The standard larger sizes use a 1-inch multi-fit thread.
Yep.
I want to highlight the term multi-fit here because it sounds like a small detail, but it actually solves a massive headache on the factory floor.
Standardization is an absolute nightmare in industrial engineering. You have American machines, European machines, legacy equipment from 40 years ago, all using different thread pitches.
Exactly. A maintenance worker doesn't want to carry a bucket of 15 different brass adapters just to install a breather.
It's a huge waste of time.
By engineering a multi-fit thread that is compatible with various standard pipe threads, you are eliminating failure points and saving an immense amount of labor time.
But the physical connection is really only half the battle. We also have to look at the chemical compatibility profile listed here, because this is what truly makes these breathers ubiquitous across every major industry.
Right. The sheet says they are compatible with all mineral oils, most synthetic oils, and diesel fuels.
Consider where these devices live. They sit directly on top of hydraulic reservoirs, giant diesel fuel totes, and synthetic oil drums.
Okay, so they're right in the thick of it.
Yeah, and the vapor fumes coming off of hot synthetic oils and diesel fuels are highly chemically reactive.
I didn't even think about the fumes.
If you put standard commercial plastics or a cheap rubber gasket over a tank of hot synthetic oil, the fumes alone will literally dissolve the seals and melt the plastic from the inside out.
That is terrifying. Which is why the internal O-rings and gaskets aren't standard rubber.
No, they can't be.
The spec sheet lists Buna N and EPDM elastomer. Buna N, or nitrile rubber, is incredibly resilient against petroleum-based fuels and oils.
Very tough stuff.
And EPDM is famous for its resistance to extreme heat, ozone, and harsh weather conditions.
You are building a fortress that has to protect the oil from the outside environment, but it also has to protect itself from the toxic environment of the oil it is guarding.
It's also worth pointing out a small compliance note here. The sheet highlights that all models are REACH compliant.
Which is important.
Yeah, this means they meet strict European Union regulations regarding the registration and restriction of chemical substances.
Right.
It proves these aren't just durable pieces of hardware, but they are manufactured with a baseline of global environmental and health standards in mind.
It is a brilliant piece of holistic engineering. They've thought about the microscale filtration, the macroscale fluid dynamics, the material science of the housing, and the chemical resilience of the seals.
So bringing this all together, we started today with a dense stack of technical specifications. Dimensions, airflow charts, pressure drops, chemical lists.
A lot of numbers.
But what we've really uncovered here is the anatomy of the ultimate industrial shield. The next time you are driving down the highway and you see a massive wind turbine spinning in the distance, or you walk past a heavily guarded power distribution center.
I want you to look past the giant steel gears.
Exactly. I want you to picture what is happening on the microscopic level. Picture these tiny, transparent lungs sitting on top of those massive metal beasts.
Vanguard.
They are standing guard against blistering heat waves, maintaining an impenetrable 3-micron glass wall, and carefully calculating the exact fluid dynamics of every single breath the machine takes. The blue to pink visual sponge is silently trapping the moisture so that the heavy infrastructure powering your daily life just keeps running perfectly.
It really is a masterclass in problem solving. But, before we wrap up this deep dive, there's one final detail on this tech sheet that I think puts everything we've talked about into a rather profound perspective.
Oh.
Yeah, it's buried all the way at the very bottom of the document in tiny text under Note 1.
I must have missed that one. What does it say?
It says, quote, "Small variations in the manufacturing process can be common and will be within the allowable engineering tolerances."
Allowable engineering tolerances. That's a very specific phrase.
Think about the juxtaposition of everything we just spent the last 20 minutes dissecting.
Right.
We are talking about enforcing absolute filtration down to 3 micrometers,
Yeah.
catching objects smaller than a human blood cell.
It's incredibly precise.
Very precise. We are measuring exact pressure drops down to a single pound per square inch to calculate precise maximum airflows. We are utilizing glass-filled nylons and specialized elastomers to demand near-perfect performance from these devices to protect machines worth tens of millions of dollars.
And yet,
the engineers who designed this system wrote an explicit, humble reminder into the very core document. Small variations are common. We have to allow for them.
that is incredibly striking. The relentless, rigid pursuit of the absolute paired directly with the quiet acceptance of the variable.
It poses a fascinating philosophical question for you to mull over after you finish listening. In a world and in a life, really, where we constantly demand absolute perfection to protect the things that are most vital to us, we still inevitably must accept the physical reality of allowable variations.
Wow.
It is a powerful reminder that true engineering, true resilience, is never actually about achieving flawless, unattainable perfection. It is about brilliantly managing the imperfection.
brilliantly managing the imperfection. That is a truly perfect thought to end on. Thank you so much for joining us on this deep dive into the invisible lungs of the industrial world.
It's been a blast.
Until next time, keep looking closer at the world around you and the machines you rely on, because you never know what invisible microscopic battles they are fighting just to keep the lights on.